Another interesting result for analyzing numerical methods is the Taylor expansion. The Taylor expansion it shows to us how to approximate any function that does not behave in a string way, so that does not have singularities or something like that. So the Taylor expansion is showing us how to approximate any function with a polynomial. And in order to do that, you just have to follow the results that we do have here. And actually, the Taylor expansion is done at around 1 point. In this case, we are going to call x0. So the function is equal to the function evaluated at x0 plus the summation of different terms from n going from 1 to, in principle, if we want the summation or the expansion to be exact, so the summation here has to be extended up to infinity. But usually, in order to practical way, we have to cut somewhere, so we'll consider n terms, n capital terms in the summation, and each summation corresponds to the following expression here: 1 over n factorial, the nth derivative of the f function with respect to x evaluated at x0 times x minus x0 to the n. And then this term here that corresponds to the error that we are considering whenever we cut this summation here at the capital N, so that the error goes like the n plus 1th power of x minus x0. That basically means that the higher the number of the terms you're considering the summation here, the wider is going to be the validity range of the expansion you are considering here. But the best thing to do that, I think it will be to do an example for that. So let's consider that we do have, for example, this function here, and we want to approximate that function with a polynomial of different orders, just using the Taylor expansion. So for that, basically, we will have to follow this expression here, and we are going to do this expansion here around point x0 here. Okay, so basically, we have the first term here will correspond to the function evaluated at point 0 in this case. That if we substitute that one, the goal will be 1 minus 2. So the function evaluated at 0 will be minus 1. Then, in order to consider the next term, which is going to be the linear term that corresponds to n equal 1 here, we'll have to check or have to calculate will be the first term in the summation will correspond to n equal 1. And for that, we have to calculate the first derivative of the function with respect to x evaluated, in this case, at 0. So if we calculate the derivative of f with respect to x, we'll have minus 2 over 2x plus 2 over minus x, and if we evaluate that at 0, we have that this is 0. And this actually we expected, because if we consider the geometric interpretation of the derivative here, you can see that the geometric tangent of at point x0 to this function is parallel to the x-line, so that you can see that the angle that's formed between the geometric tangent and the positive direction of the x-axis is 0, so the tangent series will be 0. So therefore, the result goes correspond to what we expected considering the geometric interpretation of the derivative. So we don't have a linear term in this Taylor expansion. We have to go to the next order, and in order to do that, we have to calculate the second order derivative of the f function. So basically mean this is 4 to x minus 2 minus x. So we evaluate that at x0. We have that this is 2. So this is 2. So, and we consider that the n equal 2 term, we have a 2 factor which is also 2. So we have that the function, as considering the quadratic approximation, can be approximated with the following expression, which is the function evaluated at 0, which is -1. The linear term is 0 in this case because, again, the derivative is 0. And then we have that the next term will correspond to the quadratic term, which is 1 over 2 times 2. It's 1 times x minus 0 to the second, which is plus x squared. And the error in this case is going to go as the power of x, the third power of x. So that's going to be the approximation. We can approximate, therefore, this function to the second order with this parabola here. It's going to be something like that. But we can see it much better just using mathematics or MATLAB to represent this function here. Here we do have the results here. Here, this is the result I got. This is the parabola we got before. And this is the quadratic approximation, the second order approximation to the function here using the Taylor expansion around x equals 0. You can see here this is the parabola, and that will be the validity range. You can see that very close to the x equals 0, you can see that the parabola fits very well with the function we do have. Of course, this is not finished because you are making an error, and if we are the farther we are going from this from the 0 point, you can see that the error you're making is bigger. So in order to decrease the error, what you can do is you can go to the third power, and if just using the Taylor expansion, you can easily check that the third power approximation for the function is going to be this one. As you can see here, you can see this is the cubic polynomial you are getting, and this is the exact function. You can see that the validity range, in this case, you're increasing the validity range, and going to the full power, that will be the result that we do have. Again, the validity range increases with the power of the polynomial. And if you go to the 8th order, for example, you can see that you can almost distinguish. It's almost indistinguishable in this range of x. Of course, going to this x higher, you can see that it starts to separate, the approximation starts to separate from the exact one. But in this range, for example, you can see that the blue line goes over the red line, which making the approximation very accurate in this range. So the Taylor expansion, again, it's a very useful tool when dealing with numerical methods, and it allows us to approximate the function whenever. It doesn't matter what kind of function we have. It's important not to have singularities. I mean, basically what's important is that the derivative of the function, any other derivative of the function has to be well defined, so it's important not to have singularities. So whenever we do have such kind of function, we can approximate that to any polynomial of different orders, and the validity range of the of this approximation will increase with the order of the polynomial you are considering for the Taylor expansion.